Hello and welcome to a look at the introduction and to the first part of the uncertainties and errors. We're looking at this as part of the topic 1, but this is one of those things that you might want to come back to several times throughout the course whenever you're doing practical work, because really we're looking at data analysis here. Now you might have some opportunities to analyze data that you have not gathered, but certainly whenever you gather data, you'll have to do data analysis and look at the different things that you've made and how you're going to make them work. So this uncertainties and errors section, we've split it up into 3 parts. We're going to start by introducing precision, accuracy, random and systematic errors. Then we're going to look forward at how, once we've got a set of uncertainties, how we propagate them, how we move them forward through calculations. And then we're going to look at the role that uncertainties and graphs have to do with each other, how uncertainties inform how you do your graphs, and how from your graphs you can determine further processed uncertainties. This is the sections from the IB Physics Guide. So just today, as I say, we're going to start with random and systematic errors and absolute uncertainties. And on the right-hand side there, you can see some of the skills that we're going to look at. We're going to start by introducing you to 2 concepts of precision and accuracy. These are both words that you might use in everyday life, and in such you will probably find that they have very close meanings. In physics, in science, they do have very precise meanings which aren't, they're close, but they're not the same thing at all. Precision comes from repeating. You cannot take one measurement and then say whether it's precise or not. That's meaningless. Precision comes when you repeat measurements, with everything being the same. So in scientific terms, you haven't changed your independent variable, you haven't changed your dependent variable, you just keep on taking more measurements, and all of the control variables stay the same as well. So if you do that, then you have a precise set of measurements if they're all pretty close to each other. That's a judgmental call, of course, how close is pretty close, but that's the basic idea. If your results are more or less the same, then we say that you have a precise set of measurements. The analogy here is with shooting arrows, and if all your arrows hit your target at more or less the same point, then you have a very precise set of shots. Accuracy, on the other hand, refers to how close you are to the actual value. So in physics, whenever we take a measurement, there is more or less the perfect answer, and your accuracy is how close you are to that perfect answer. If you're taking repeated measurements, then it's a little bit more subtle. It's how close you are on average. So if you look at that example on the right, again going with the archery example here, those 4 shots aren't necessarily that close to a center, but on average they are. They have some random error creeping in there, but on average the aiming is pretty good. Similarly, if you take multiple readings for a measurement, they might vary with one another. They might vary quite a bit, but as long as they're spread out over the actual value, and the average will give you the actual value or very close to it, you can still say they're accurate. So the important point is that you can be different in your precision and your accuracy. So these points over here were quite precise, but they weren't accurate. They weren't hitting the center. Okay, so similarly, you can have a repeated set of readings which are very close to each other. They can be precise, but they're not accurate if they're not actually close to the correct value. Similarly, these ones are accurate in that their average value is that of the actual value, but they're not very precise. They're actually quite spread out. Ideally, when you do a lab and you analyze your data, you want results which are precise and accurate. And what you really don't want is ones that are not precise and not accuracy. But by the way, if you could ever pick one, then accuracy is what you want to go for, because accuracy gives you to the right place, and you can use tools such as taking averages to find the appropriate value. If you're not accurate, if you're not actually measuring the appropriate value, it doesn't really matter how precise you are, because you're just going to be wrong, and it's much harder to see. So high accuracy and low precision on the top there. high precision but low accuracy at the bottom. So why aren't you always going to hit the same spot on that target every time? Why are your measurements going to vary? Well, random error is the most likely cause. Depends on the actual experiment that you're doing, the measurement that you're taking. But if you imagine a situation such as a bouncing ball, then every time that ball bounces, even ignoring longer term effects such as the fact it's losing energy, every bounce is going to be slightly different. Every measurement is going to be slightly off. Minor changes in the controlled conditions, minor but random inaccuracies in your measurement, all these contribute to the random errors. When we're doing random errors, when we're estimating what those random errors are, the first thing we look at is the tool that we are using. If you have a centimeter measured, if you have a ruler marked out in centimeters, then the closest you can probably get is about half a centimeter. So about half of a division. If, however, you have a digital tool such as a scale with a plus minus value of 0.01 grams, then the most precise that tool can be is plus minus 0.01 grams. So go with that value. If you're not sure, go with this, if you've got like a choice of two, go with a bigger value. Or it's always better to overestimate your errors than underestimate them. But beware also that even if your instrument is technically capable of a higher precision, you might not be. Depends how you're using it. It depends on the method and the process. So, for example, if you have a stopwatch which might well be accurate to 100th of a second, that's great, but you'd be wrong to put down plus minus 0.01 seconds because if you're starting and stopping the stopwatch by yourself, are unlikely to be that accurate. But do be creative in your techniques. If you were to put a stopwatch next to your experiment, set it going, and then use a camera to take a video of an event with a stopwatch next to it, which you can pause and rewind and play. That way you might be able to become much more accurate than if you were just trying to start and stop your video by hand. If you do know that you have random errors, and you almost certainly will, you repeat your measurements. And that's why we try to specify a minimum of 5 repeats, 5 different trials for every experiment in science and particularly in physics. So that's how you get the average. But how do you get like the plus minus value? Well, we've already said you can do it using your method, your tool. But once you've got a set of values, you've actually got more information to use there. Whatever you do, you always choose the maximum possible random error, the maximum possible uncertainty. We'll see what I mean in a second. So find the range of your measurements, largest value, and divide by 2. And that is the plus minus value you use, as long as that is larger than the measurement uncertainty you worked out here. If this value you worked out, the measurement tool uncertainty is larger, if you worked out your timing is accurate to plus minus 0.2 seconds, and all of your results were within 100th of a second, then you might go, well, that might be just a lucky coincidence, and you go back to the larger one, which would be the plus minus 0.2 seconds from your process. If you have 5 trials or less, then that range divided by 2 is probably the best way of doing it. If you have more than 5 trials, you can be a bit more sophisticated and calculate something called the standard deviation. If you're watching this video near the start of your grade 11, or however you want to call it, but your IB diploma year 1, then you probably haven't looked at standard deviation in mathematics yet. I'm sure you will. But you can have a spreadsheet calculate the standard deviation for you. And again, just compare that value to the measurement uncertainty and again, use whichever is larger. This will hopefully make more sense with an example. So here is a decent looking data set for a pendulum. Okay, so pendulum is swinging backwards and forwards, and you have a timer which you estimate is accurate to the nearest 0.3 seconds. I should have said plus minus 0.3 seconds. I missed off the plus minus sign, sorry. And you're calculating 5 swings because that's easier than just trying to calculate one swing because it happens very fast. depending on the length of your pendulum, and you've chosen 6 different lengths of a pendulum varying from 0.1 to 0.6 meters to an accuracy of 1 centimeter plus minus 0.01 meters. The only other thing I'll point out about this table is that look at the consistency. The number of decimal places in each column is the same. The number of decimal places in the periods is the same number of decimal places as in the uncertainty, and ditto for the length. It says 0.10, 0.20, etc. because the uncertainty in length is plus minus 0.01. Same number of decimal places. And finally, notice I've labelled it table 1 and I've given it a little description. That's something you should always do for all of your tables and graphs. So that's our data. What do we do with it? Well, first thing we do is we calculate an average to give us an average. So there you go. On the left you have the raw data table and the second data table, and I've labelled it table 2. I've called it the process data table because that's what it is. I've calculated an average, that makes it a processed data table. Now I need an uncertainty in the average for 5 swings. I'm going to do this using method 1, which is the range divided by 2. So for my first row, length of pendulum 0.10 meters, the average is 3.1 seconds, the average time for 5 swings. Notice that my biggest value was 3.6 and my smallest was 2.7. That gives a difference of 0.9, 3.6 minus 2.7. Divide that by 2 gives me 0.45, which I'm going to round up to 0.5 for consistency here, to give me 0.5 uncertainty. Okay, you're always fine to round up, never round down. For second row, 4.4, 3.9 is a 0.5 range, divided by 2 is 0.25, round up to give me 0.3. 6.1 to 5.1 is a whopping 1 second of difference, divided by 2 gives me 0.5. 6.9 minus 6.2 is 0.7, divided by 2 you get 0.35, round that up you get 0.4. 7.9, 7.0 is 0.9, divided by 2, 0.45, round that up we get 0.5. And my last row is a bit more consistent. 8.1 minus 7.7 is 0.4, divided by 2 you get 0.2, so I write down 0.2. But hold on, 0.2, which I've written down here, is smaller than my measurement uncertainty, which you said was 0.3 seconds. That 0.3 seconds is a hard limit, okay? I could have all the same number by just coincidence, but I still know that my uncertainty is actually 0.3. So I replace that 0.2 with 0.3. And now I have a set of uncertainties. That's method 1. I could do the same thing by method 2. The equation for calculating standard deviation is up there on the right hand side, but say don't not worry about that if you have not done it yet in mathematics. Instead, you can just use stdev in Google Sheets or Microsoft Excel in order to calculate a standard deviation for you in your spreadsheet. And you can do that, and it gives you this set of values here. Standard deviation uncertainties tend to be a little smaller. The range divided by 2 tends to capture a bigger uncertainty, be a little bit more uncertain. I tend to go with a bigger uncertainty if possible, purely because it makes working with the graphs a bit more easier, a bit more realistic, and it gives you more chance to operate the skills. But if you've got a good set of data, and really 5 trials isn't probably enough, it's marginal. If you've got more than 5 trials, then standard deviation is probably the more sophisticated method. Although it only works if you genuinely have random error. It has to be a random distribution about that average. Oh, but do notice that the same rule still applies. We use the method if it's the greater value. So anywhere I've got less than 0.3 in that table, I have to replace it with 0.3. which I've done there. Okay, so that's given us 2 different ways of calculating an uncertainty in our average values. Before we go, systematic error. So random error is those sort of set of random errors that are just impossible to avoid. A systematic error is a bit more evil. Systematic error is used when you are either using a measuring device which is broken in some way, either physically broken or just consistently giving you the wrong answer, or it's badly calibrated, or your method, the way you're using something is wrong. For example, if you're using a ruler and forgetting that it doesn't necessarily start on 0. Okay, so and other reasons, other causes of systematic error might be if you're reading a level on a measuring cylinder or something like that, or you're looking at a dial instrument such as an ammeter or voltmeter, and you're not looking at eye level, you're not accounting for parallax when your eye is not totally aligned between, say, the needle and the scale, or the meniscus and the scale. That will lead to errors. And it will lead to systematic errors if you're always looking down, or I guess up, but if you're always looking at a particular angle, you're always going to be off by about the same amount. Okay, so some other examples there. Systematic errors are very hard to spot. They're not like random errors. Random errors, you can kind of see that they're there because when you plot them, they kind of spread out. Systematic errors, about the only way you can tell is just by being really careful, by double checking your data, and occasionally by looking at graphs and just noting that something is wrong. So for example, we'll look at graphs in more detail later, but suppose I was plotting an object's movement and it's traveling at a certain speed, and I plot how far it's moved at certain times after it started moving. When I get that data and I see a nice straight line, which is what I'd expect for something of constant velocity, but it doesn't go through 0, 0, which is weird, because when the time taken was 0, the distance moved should have been 0 because it hasn't started taking it. So if you see something like that, then you know that's your observed results and that's your expected results. That's a good sign that maybe something wrong in your experiment. Unfortunately, unless you can find a clear and numerical reason why you got it wrong and by how much you got it wrong, you probably will need to take your data again in that case. Okay, so we've looked at random and systematic errors. We've talked about absolute uncertainties, those plus minus values with the same unit as the measurement. They're absolute uncertainties, but we'll look at more detail next. And we've said how that we can use an uncertainty range by expressing it as a best estimate, then plus minus the uncertainty range. Okay. Thank you. Thank you. Thank you.